Good morning. Hi, everyone. I hope, good morning. Hi, Robin. Always good to see you first in the chat, too. Let me rearrange my windows and now I can see all of you.
Mhm.
Good morning. I know. um, that's um, a very good morning for the last day of the week, right? Yeah, good morning, Ayla and Mehmet and Saja and Daniela. Good morning to you all. I hope you're all doing well. We made it to Thursday, and this is great. It's the end of the third week, which means we're about to be done with about 60% of our class. So imagine if this were fall semester, today would be like the beginning of November, very very end of October, beginning of November. Yeah, wow is right. You know, these winter courses are not for everyone. It's really fast. You have to hope that nothing goes wrong in life because there's no time to catch up. So yeah, we've made it. Yeah, we're doing all right. um, yeah, so happy Thursday, everyone. I hope today is smooth. We only have chapter 9 to go through. Good morning, Nathan. Good morning, Keon. Yeah, we only have chapter 9 to go through, and it's not very much. We won't do the full chapter. We'll do the parts that you really need to know to continue on in physics and in your other courses. Um, so,
Ask a question about that. Like, so I know in number on chapter 8, like when I went to the homeworks, I saw that like we really only needed section 1, 2, and 5. Does
mhm,
that sound right?
yeah, sounds about right.
Okay, and so like it's not weird that we skipped 3 and 4. That's not
Nope.
okay. And so like for chapter 9, would I like can so sometimes the chapters don't give the like the section that you're doing, you know?
Mhm.
Like sometimes the problems don't. So like it's chapter 9, we'll be able to tell from the lecture. It'll say like 9 point whatever in the figures and stuff.
Yeah,
Okay.
yeah. Um, and then Henry says, "I spent all day yesterday doing the wrong homework." Oh no, that's a bummer. But let me tell you, you did physics. But yeah, that's a bummer. Um, yeah, sometimes it just happens. Pay like special attention always to the instructions. Yeah, that sucks. But it's okay. You'll be really good at torque next week when we get to will help you. Okay. Oh no. I just got that symbol, that thing. Yeah. I froze for a second, I think.
Yeah, while you were laughing.
Oh no.
It's like, ha, 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 ha.
Oh no. Yeah, I just got it on my screen. It said internet unstable. So we're just gonna go with it and see what happens. Yeah, I know earlier this week I had trouble in some meetings, so yeah, let's just go with it. I don't think the chapter is very long, so maybe we'll even finish before 12:30. I'm not sure. Um, yeah, I do have somewhere to be today, and I have to leave, so I can stay for a few minutes after class, but not very long. So just be ready to email me if you need anything, if you need anything at all. Okay, I think we can start chapter 9 and really complete our description of motion. Yeah, some cool history to look at in chapter 9. Let me set up my screen and I will share it with you guys and we will get to it. To all 18 of you on the call, I'm really glad you're here. And you know what I was thinking of doing too is correlating the level of participation in Zoom to the grades. And I think, for some people, you don't need any participation and you'll do well. Online is for you. But I really, it probably really helps to be engaged in class. And it's hard to be engaged here. But um,
When I'm not engaged, I fall asleep.
yeah, yeah. Yeah, I have to take notes when I'm in other meetings because I'll stop paying attention and I have to like flip my phone over so I don't look at it. I have to do all kinds of things to like pay attention. So I get y'all. But you know, we're adults. We got to get through it and you know get one step closer to our goal of finishing this class, transferring, getting a degree, and starting a career. So it all plays a role. It's worth your effort. Um, so today's chapter 9 is going to complete our view of motion, and really, I hope it makes it makes the idea of motion more or it makes the idea of motion closer to what you really thought motion was. Instead of just constantly thinking of change of position over time, it goes back to that question that we asked ourselves in chapter 1, right, or in chapter 2 and 3. Which would you rather catch, right? If they're all coming at the same speed, a bowling ball or a basketball or a tennis ball, right? Which of the ones would you rather catch? um, that's where this chapter will kind of take us with the idea of momentum. So before we get to the actual equation of momentum, we look at situations around us, and a common scenario is the situation of collisions happening. And so we know collisions as accidents in everyday life, but collisions are happening at smaller scales all around us. And a really great example is on the pool table, right? So here you see the setup of 3 billiard balls, and we have 2 balls, the yellow and the purple, that are at rest and they are touching each other. And so you set up your cue ball ready to strike, and you make this straight line from your cue ball, from the center of your cue ball, and direct it to the center of the other 2 balls, right? So as soon as you shoot that cue ball, at a very instant in time, when the cue ball touches the other two, the 4 and the 1, the purple and the yellow ball, at one moment in time, you can draw a straight line through those balls as the cue ball contacts the 2 balls. At the very next moment, what do we see happen? We see a pause, and then we see a very, very quick instant pause. And then we see the yellow ball take off. The cue ball makes a direct hit, and it centers all of the balls for a very, very quick moment in time, and they're all lined up at that moment. But what happens is that the cue ball stops, and only the yellow ball moves away from the collision, right? The purple ball is still there, and only the yellow ball is the one moving. So it makes you think, what happened to the motion? What is happening? And you guys may have seen this too with those, what's it called? I think it's the cradle, Newton's cradle, where you have those metal balls swinging, and you have some, yeah, you have so many in line, and the only ones that are moving are the ones on the end, right? And pay attention to this when the next picture I'm going to show you. The balls are all going to break, but pay attention to ball number 15 in the center. Watch number 15. Everything breaks apart, but 15 pretty much stays right there in the center. You'll see it again. It even spins around a little bit and only moves position later when something else hits it. So what is it that's happening? What is it that's moving around? We have an idea that we can describe motion with kinematics, and we have an idea that we have some form of energy that's involved too. So we're going to take all of the concepts that we've talked about, Newton's laws of motions, the idea of conservation, and we're going to bring it in and study this situation of particles moving and how they interact. We're going to analyze it using Newton's laws of motion. So the next 3 or 4 slides are derivation. You don't necessarily need to have it memorized for my class, but I want to show you where the equation for momentum eventually comes from. Okay, so let's look at a scenario similar to the pool balls, but now 2 particles in space and nothing is around them. There's nothing in their system. The 2 particles with nothing, no external forces acting on them, we could say the force acting on them is something like a gravitational force, because that's internal to the system. So let's say that there are gravitational forces. Because the two particles, mass 1 and mass 2, have a mass, we know they're going to gravitate towards each other, right? That's the idea of a gravitational force. So we can start analyzing the situation by looking at what is the force there and what is the result in motion afterwards. We see that because of Newton's third law of motion, we can look at the first force for mass one, right? Mass one is going to exert a force onto mass two that is going to pull mass two towards mass one. It's going to gravitate towards mass one. That's the gravitational force. When that interaction happens, mass two is going to take off with some velocity because of that impact, because of that collision that occurred. And so using Newton's third law, we can also look at the opposite force, that the perspective of mass two then. Well, if mass one exerts a force onto mass two, we know that mass two also exerts a force onto mass one. And here they are. You see them both here. And because of Newton's third law, we know that they're equal and opposite to each other. So that's all fair. Now we want to think of a little bit of our ideas of what is happening in total in the system. What is the total change occurring to the system? Is there any change happening in terms of the forces? And so mathematically, what we would do is look at this as an equation and start to move around the variables and see what do they sum up to, or what is the change, if any. So we move this over to the other side, and now you see that the two forces that are equal and opposite will sum up to no change, right? There's no change in terms of the forces that are going to occur. So in the system's point of view, if we add up these forces on the particles, the total sum will be zero. And this lines up with the idea of us having this isolated system for this model that we just created. So this is fine. We looked at the sum of the forces. Thanks to Newton's third law, we can say equal and opposite exists here. Notice we from the image, we can't say much else, right? We know that they're going to interact, they're going to hit, and they're going to move in some different direction. So our next step then is to look at Newton's second law and see if Newton's second law, now that we have forces, and remember Newton's second law is all about forces, F equals ma, what else can we say about this? And so we're going to pull this over to the other side. And now we're going to look at that same equation, F12 plus F21 is equal to 0. And now we're going to put Newton's second law in. So here's what we had on the other side, right? The force that mass 1 exerts onto mass 2 plus the force that mass 2 exerts onto mass 1. And so you see that the masses here are at the center of the equation. And then we're looking at the way that mass is going to accelerate. So we want, our goal eventually is to get this to somehow match the components of what we're given and what we know in our model. So we don't have acceleration in our model, but we do know that there's a velocity, some speed that we know the particles are going to change by. So that's our next goal, is to look at this equation and see where is velocity and how can we bring velocity in. And so here you see it in acceleration, right? We know what is the definition of acceleration. It's the change of velocity over time. So our next step is to bring in that definition of acceleration. Okay, now here's where we're going to start playing around with the math that's going on. Our understanding usually of a derivative is whenever there's a constant, we pull that constant out, right? Because the constant won't affect the answer or the situation. It's only going to change it by some factor, some constant of some sort, 2, 3 times, 4 times. So if mass is a constant, we are able to pull it back into the derivative, because this will help us physically describe what's happening. So we're going to take this constant, it's going to remain a constant, but we're going to pull it back into the derivative. And so here it is. Mass goes back into the derivative. It acts just the way it did before. And now we can redistribute this derivative so that it's, not redistribute, but regroup it, right? So that the equation looks a little nicer for us, and we take the derivative out. And so we see now that the derivative here is mass 1 times v1 and mass 2 times v2, and the whole thing is equal to 0. So when everything here is equal to 0, we're saying that as things change in time, however it changes in time, the result is 0. And this is very similar to our idea of conservation for energy. But we see that this is an energy, right? So in energy, the total energy of an isolated system is constant over a time interval, which results in the energy being conserved. So whatever these quantities are, they are being conserved because the derivative results in a constant, which is zero here. And so this is where we now want to make a definition of some sort. What are these two sets of variables that we've come up with? Well, it turns out this is our idea of motion, and this mass 1 times v1, or mass times velocity, is our definition of linear momentum. Notice that it's a vector. Okay, so we're going to pull it over to the other side. So our definition then of linear momentum, mass times velocity, is represented by this bolded vector p, little p. And so the linear momentum of a particle or an object will be modeled as that particle's mass moving with some velocity v. And this is defined by the product of the mass and the velocity. And so the linear momentum is defined as the scalar mass times this velocity vector. And so momentum is a vector. We know what happens when momentum is a vector, right? When momentum is a vector, like in a vector, we can break it up into its components. So we have, and we can break this up into its magnitude in the x direction, its magnitude in the y direction, and its magnitude in the z direction. So now you have the mass times velocity in all directions. And what's really nice is that here you can make a distinction for how something moves, what is its momentum, based on its mass, right? So momentum gives us a quantitative distinction between heavy and light particles because of this mass that's here. We can now say if something is heavy and has a large mass, it's going to have a large momentum. And if something is light and it has a very light mass, a very low mass, it's going to have a lower momentum, keeping the velocities the same. So here now we can describe a little bit more intuitively, the magnitude of momentum of a bowling ball is much greater than that of a tennis ball or a basketball. So the reason you'd want to catch the tennis ball versus the bowling ball is because the tennis ball is going to have less momentum. It's a little harder to think about it in terms of force and acceleration and mass because you have to make those relationships really quickly. But this I hope helps you think of motion a little bit better. And in fact, here's the historical part, that when Newton was coming up with his laws of motion, and he had lots of inspiration from many scientists, philosophers from thousands of years before, literally 2,000 years before, but there just wasn't enough backing for it and enough math to prove it, right? But when Newton described the idea of motion, he wasn't describing the change in position over time. He was in fact describing the idea of momentum. And so this was the initial idea of motion. So when we think of things moving, we say it moves at a certain speed, and we say that it is defined by its mass, right? And so this is what's so nice about momentum, is that you can tell how is it moving, how fast and how slow, and then you can also identify it as its mass, its object. You identify it in the world of things that we can see with our eyes, like large scale things, by how heavy or how light something is. So this is it. This is the actual quantity of motion. And they didn't use the word momentum. They used a different word. Not acceleration, inclination doesn't sound like something we'd use now, but yeah, I think the original wording was not momentum, but something like that. Okay, so, oh my goodness, I did not open my chat window. I'm so sorry if I missed any comments. Okay, let me fix it. Oh my goodness. Okay, you people here. Oh, it's just about beer. If I wasn't on camera, I'd be drinking a beer. Oh, that was from earlier. Okay. And then yesterday, that random noise, that person isn't in our class, I think. Oh, Daniela, very good.
Oh, yeah, I watched the lecture, rewatched it, and it cracked me up again.
Yeah, if maybe I should figure that out because that wasn't good. Yeah, and Sandra was thinking the same thing too. Yeah, these random noises and all of that, it's so weird just being on Zoom. I'll tell you guys something really quick. I'm planning to move my desk around because right now I see my wall and you guys see everything behind me. But I have this like tendency to like keep looking over my shoulder like someone's gonna come in, but no one is, you know? Um yeah, so these random things and these random like me just constantly looking because I'm not in a classroom, it just this is weird. Yeah, I haven't had a Zoom crash yet. Someone crashed my Zoom call, but maybe that was it yesterday. I'll rewatch it, or if you guys do it, find out. Let me know too. Um, I don't know. Momentum's pretty cool. They could come in and learn about physics. Um, okay, so now I have my chat window open. Oh my gosh, Keon says lock and bolt the doors. Guys, this
There's
happened.
windows behind you, you know, it's possible.
Yeah, this happened to me last semester. It wasn't during Keon's class, but during my fall physics 101. I never close my doors when I'm in my apartment, and this time I happened to just close my office door, and for some reason I also happened to lock it. And I'm in the middle of lecture with, you know, like you guys, and in my office I hear someone knock on my office door. Keep in mind, I live alone. I live alone. So someone came into my apartment, knocked on my door while I'm in lecture, and I had like a neck back pain for 3 weeks because I was so scared and stressed out. It was horrible. Yeah, it was really scary. I mean, I should stop mentioning it because I always get like this chill down my back when I talk about it. It was scary.
My old
Yeah.
apartment, someone walked in and like started sleeping on my couch, and I woke up. I lived in a studio, so my couch was really close to my bed, and they were sleeping on my couch, and I was like, "Who are you? What are you doing?" They had like chains with them and stuff. They broke in my back door.
It's wild. The things that happen out there are wild and you just never know. It's good to live in a world of, you know, we think positive things will happen, but let's be real, sometimes things happen. You just gotta be, yes, you gotta be ready. It's life in the city. Mind your business. um oh yeah, I have pepper spray, right? Oh my gosh, Henry. Yes, you guys, we gotta be really careful out there. Wow, my God, the things that happen to all of us. So this is another reason, guys, to just always forever. Oh God, if you can't see the video, Keon has like these, like medieval, I don't know, like, like what are they? Knives, swords, something.
They're called Sai. My neighbor moved out and he gave them to me. So he gave me those and some nunchucks. So it's pretty fun.
And the nunchucks. Wow. Oh man. This is quite a tangent, guys, but it's all good. This is a reminder to forever, ever be kind to people because you never know what they just went through a few minutes ago or the day before. And I always say everyone acts a certain way for a reason. They didn't just wake up being that way. You know, they act that way for a reason, and we gotta think about that. Yeah. Okay, let me chill for a second. And we'll get back to this momentum. The good thing is that for this idea of momentum that we're working on here, everything that we've done already with the study of velocity and with vectors, all of it applies here. So we're gonna practice it and bring in some bring in some more wildness into physics. I'm gonna think about these nunchucks some more. I think I'm gonna watch some videos afterwards. Oh God, there they are. If you can see Keon on video. Yeah, we'll see those nunchucks again. Okay, so let's continue with momentum and see what more we can say about this. So we've looked at momentum in terms of the velocity and the mass, and now we want to see if there's any way that we can relate this back to chapter 5, Newton's laws of motion and the Newton's second law, the one that then does tell us a little bit about acceleration and force and what we can do. And so here's how we're going to connect it. Of course, we start with Newton's second law. So if we look at the resultant force that's acting on the particle of the momentum in the system here, we could start with Newton's second law, the sum of forces equal ma. And again, we can rewrite this acceleration in terms of what we have in our figure, which is, you know, the velocity, something that we can measure a little easier. Once we rewrite this as mass times the change in velocity and over the change in time, you can recognize that we can move that mass value back into the derivative again, right? And now we can write this mass times velocity as this momentum here. And so here it is, guys, the sum of the forces, or the force, is equal to the derivative of the momentum. How the momentum changes is due to a force, just like how the velocity changes is due to an acceleration, which is caused by some external force. So now we have several ways of saying this. So the time rate of change, or you can say the rate of change. This is common whenever you see rate of change, you think change over time. The time rate of change of linear momentum then is equal to the force that's acting on the particle. And I think that should make sense to us, right? If something changes its motion, it's because something acted on it. And that thing that acted on it is the force.
Does this mean that, like, so did we take out the DDT since it's on both sides?
No, this equation here is equivalent to this and just written in a different way. It's just continuing the line of equation.
Oh, okay, I see what you're saying. Okay, so it's not saying that, like, the change of mass times velocity is equal to, well, it is, because it is.
It is, but they substitute each other. We're just rewriting it. But I hear what you're saying. You're thinking that the full equation is this, and we can just cancel out the derivatives. Yeah, just the way that they write these things in one line can certainly cause that. And I'm here to translate what the textbook is showing you. But yes, this is the equation. And this comes from the original equation of the change in mass and velocity over time. And so what does this also do for us now? Besides giving us another way to solve for momentum, we can also, in more complicated scenarios, we can also now account for a change of mass in a scenario because we pull that mass into the derivative. And although it's a constant, there are physical situations in where it's not a constant. And then you'd have to calculate for how the object is able to move with a reduced or increased mass than its initial situation. And a good example of that is a mass of a rocket. The rocket will release fuel or use up fuel as it's burning and increasing its height. And so that'll change, right? Does this mean that MA equals D over DTP? Yeah, that's another way of writing this. That's a really good way of thinking about it too. Yeah.
So, like, the mass times acceleration is equal to the rate and change of time of momentum.
That's right. Yeah. Good ways to say it. Now, I wanted to pose this question to you guys because you're all very creative and have very different ways of looking at physics and making connections. Can you think, and let me hear in the chat or unmuting, and take a second. Can you think of another scenario that over time the mass changes while something is moving? So similar to the rocket changes its mass because it uses up its fuel. And, we have like hundreds of gallons of fuel in there, which is what Tesla's trying to get over, SpaceX people. Yeah. Any other situation we could think of?
People, like, we sweat.
Oh, yeah. I wonder that interval of time would probably have to be on a larger scale. Something like a few weeks would give us a big number, but over a while,
unless we're running, we lose a lot of mass. Like, in running a marathon, you can lose like gallons of sweat.
Yeah, that 1 hour or a few hours of running, it would be interesting to see how much our motion changes based on the mass that we're losing. Um, oh, a black hole in space. That's theoretically massless at that speed. Maybe as we're approaching the black hole, that would be interesting to look at, because the massless happens as we're approaching that speed of light and getting towards that black hole. And then that says a car. That's the one that comes to mind too for me when the car is using up the fuel. But I think a little more a little more violently. I think of an accident and like the car lost its door or something, and so that it has much less mass. Oh, a candle. A candle. That's a good one. Yeah. As it's burning, right? Or a candle with legs. Playing chess.
What about toast?
Oh, wow, you guys are coming up with some great ones. Yeah, toast, because you as you're scraping it or eating it, right? That mass is less. Playing chess, or a proverbial snowball rolling down a hill. That's a great one because
Oh
that
yeah,
mass
'cause it gains mass.
it gains, yeah. Oh, or Andrea says a water bottle while we are drinking the water. Yeah. So these are great ones, right? Situations where even though we know that in most scenarios mass is a constant, physically we have to be able to identify situations where it's not. We probably won't go into that in this class. I think you'd have to use a second derivative or a second variable or some sort of second order differential equation there, and you will do that in your differential equations classes. And that was my favorite class, differential equations and linear algebra, because you get to do like cool math to solve all the complicated situations of like pouring water into a bucket while you're at the same time, using the water coming out through another outlet in the bucket. Yeah, it seems like mind-boggling. Like, how the hell do I calculate that? Differential equations lets you account for several variables moving at once. It's good stuff. Okay, let me continue. So guys, really, really great suggestions. I'll bring this up to the class next semester and see.
Oh, chalk on a chalkboard.
Yeah, chalk on a chalkboard. It's losing its mass as we're writing. I miss chalkboards. Daniela, doesn't the spacecraft release air to keep itself in trajectory? Does it release air? I don't know. I think the thrust comes from the force of burning the fuel and of, yeah, I don't know. We gotta look that up. I don't know how significant of a role that plays in keeping its trajectory. I know what you're saying though. I see it in the movies when they pump out a little bit once they're in space already. I see what you're saying. Yeah. Okay. Yeah. I get it now. I'm
Like
thinking
to separate itself from the other part.
Yeah. Yes, the gases. I'm thinking Apollo 13 of how they had to maneuver into the right location, and they did that by blowing gas out of the tanks. Yeah. Yeah. Okay. So up until now, we see mathematically how we can manipulate the terms, and you guys were really good about making this connection that, yeah, because the force is equal the change in momentum, MA is also equal to the change in momentum. We're going to be given scenarios and diagrams and pictures, and our goal is to be able to pull information from that. So we need to really set up our frames of reference and then bring in our ideas of conservation. So this is what you'll see then on the next slide. So all we've done so far is come up with this idea that the change in the momentum is equal to 0. And let me write that one more time in short notation. The change in momentum, dp dt, is equal to 0. So this means that this 0 is a constant, right? It's a constant of some sort, and whatever changes happen, the total changes will still equal 0. So we could look at the momentum of each scenario now and say the same thing. They're equal to 0. And in words, this means that the time derivative of the total momentum will equal to 0. And so we can write that then, that the total momentum is a constant number. It's a constant number. Think about this. The derivative of a constant is equal to 0. So this total must be a constant number. The derivative of any constant is equal to 0. So physically, the total momentum must equal some constant. Now, in our frames of reference, we're always going to try to choose things that are symmetrical to each other, so that constant in our very like centered world, we want that to equal 0. We want it to cancel each other out by symmetry. So our goal is to choose a frame of reference for which the total momentum is equal to 0. And usually that's kind of presented in a normal way in a problem where you're not going to think right away about the frame of reference, but what you might think instead is, let me take these two particles, mass 1 and mass 2, and just kind of think that how can the momentum of each here equal 0? Well, you can draw a frame of reference like I did in orange here, where we center it where the interaction might happen. That might be one way to do it. And so here, with this frame of reference centered here, you can see that velocity 1 and velocity 2 and mass 2 and mass 1, the combination of them will equal each other. The momentas will equal each other because we chose this frame of reference to be centered there. But this should be common practice. The point is to find a way to easily solve a problem. Mathematically, what does this look like? If the total momentum is equal to 0, this means that the final and initials must equal each other. The total initials must equal the total finals. And so all of the components of the initials summed together must equal the components of the final, so that you have a total that is still equal to 0. And if this gets confusing, you can always think of the total or final minus initial. Final minus initial equals 0. You can bring the initial over to the other side, and then you'll see final equals initial. And so this mathematically helps us, right? Being able to say that it equals 0 and that we have a frame of reference where everything is symmetrical. And now we can write it in component form because they're vectors. And so here it is in component form. The initial in X here must equal the finals in X. The initial positions in Y must equal the final positions in Y, and then the same for the Z axis. And so what we did here was just split it up into X, Y, and Z. Things that we can do, right? So with this notation, then you can just say whenever there are 2 or more particles in an isolated system, the total momentum of the system does not change. This is very similar to what we saw in energy, right? In energy, if the system is isolated, there are no transfers happening across the boundary. And for momentum, for this to still be true, there must be no external forces acting on the system. External forces will become obvious, like, you know, another car comes into the system, or someone physically comes in and pushes something out of the way. And so this is what it looks like then in terms of the boundary. So for some isolated system here, the momentum is conserved. So the total momentum will equal 0. This is conserved. And notice that there are no forces that are coming into this boundary. This cannot happen. No external forces will be considered. Now, remember the examples we did yesterday. It really is up to us to determine what is the system. If we can determine the system to a point where we've isolated the system, we've saved ourselves a lot of math trouble, right? Because we can make everything equal to 0. So what are some scenarios in which an isolated system is, you know, has a conserved momentum? If a cue ball strikes another pool on the pool table, which is the example we saw, and then the system is the cue balls, right? So nothing is acting on them. They've been acted on before we create the system. If a spacecraft fires its rocket and moves faster through space, the momentum there is changing, but in sum, it's all 0, right? You burn fuel, you get higher, things like that.
How is it 0?
Huh?
I don't see how it's zero. This is it gives me trouble.
So what happens when you burn fuel? Does the fuel just disappear, or does the
Oh,
fuel?
so it gives you motion.
Yes, that's right. So somehow the momentum changes, right, from one thing to another. But in the total idea of like the total idea, this is my,
So would we call the system the rocket?
that's right. We would call the system the rocket.
So it
And
gave up energy to get motion.
this system is completely isolated, right? So the change in energy here is is still zero because this system is completely isolated.
Okay.
So as anything happens, we're going to get something else. So any action that happens within the rocket burning fuel, something else will happen. Whether we increase in height, whether we move faster, the fuel is going to burn with some with some chemical energy, something like that. It exchanges within that system. This is a rocket.
Okay.
Yeah.
Looks good.
Yeah. Others think it's a corn on the cob. So another example, an incoming particle strikes a nucleus. So what'll happen? A new nucleus will be created and a different outgoing particle will be created too. So if this is your original nucleus and you have some particle that's going to hit it, that's the initial scenario. The final scenario will be that particle hit it, you have a new nucleus and you have an additional outgoing particle. So the total here is equal, but there's clear differences between initial and final. But what we're looking at is the entire situation. And then the same with an electron. An electron and a positron will annihilate to form two outgoing photons. We do a lot of that in Physics 103. The photons are, your light particles. Okay, so what type, now we're gonna go into actual scenarios. I think we're still good on time, so let me put on a timer. What type of these collisions do we have? So with momentum, it's you can study the momentum of an isolated system and it's really nice. But when you bring in another particle, that's when we're looking at collisions usually and how they're interacting with each other. And the collision is one particle interacting with another by contact of some sort, right? So we're going to start looking at these collisions and we're going to start looking at them in one dimension. At the very end, I think we'll have time to get into two dimension. So this is a collision, an event during which two particles come close to each other and interact by some means of forces. And so this is what you see here. Mass 1 and mass 2 will collide. They're going to hit each other, and mass 2 is going to exert a force onto mass 1 to the left, and mass 1 is going to hit mass 2 and exert a force on it to the right. And that's what you see here. The force of 1 exerted onto 2 and the force of mass 2 exerted onto 1. Now, these collisions have two types of collisions that we can categorize them in physics. They are going to be called either a collision that is elastic or a collision that is inelastic. And these two terms depend only on whether kinetic energy is conserved. So these are the two categories, and we'll start with elastic collisions. So a collision can be elastic when the total kinetic energy is the same before and after the collision, as well as total momentum. In these situations, momentum will be conserved because we're going to think of them as isolated systems. And additionally, for elastic collisions, the total kinetic energy is also conserved. So you can write the change in kinetic energy is equal to 0. And because it's an isolated system, the change in momentum is equal to 0. Now imagine writing this out explicitly, right? 1/2 mv squared initial equals 1/2 mv squared final. And then for momentum, m1 or mv initial equals mv final. Now you have two sets of equations that you can manipulate and work with. Now, can you guys think of a situation where the kinetic energy is completely conserved, meaning When something collides, something interacts, something crashes, the entirety of the energy is converted into motion.
Oh, if you wreck into a wall, you go through the window and hit the wall.
Do you think you'll hear some sound when you go into the wall?
Yeah, never mind.
That's good, Randy, because that's the thinking that we need here, that in fact it is really hard to have in our macroscopic world a situation where the total kinetic energy is conserved, because we'll almost always have some sort of sound, some sort of heat, maybe some light or radiation, something converting. So we usually don't have elastic collisions in our everyday life. But Brad tells us, hey, an atomic collision, this is where it might happen. No, but this is true. So in everyday life, we don't really have elastic collisions. Elastic collisions happen much more commonly on the atomic scale. When we talk about the electron and the proton annihilating each other, or we talk about a particle hitting a nucleus and then you have a new nucleus with a new particle outgoing, those can be elastic collisions because you're not hearing sound, you're not losing much energy from the collision. In everyday life, we have what is called approximate, I think it's approximate elastic collisions. Very close, but not exactly. Even a bouncing ball, right? You bounce the ball. When the ball hits the ground, it's going to come right back up at you, but you're going to hear that bounce, right? And then you're also going to see the ball expanding. Other things happen. So usually atomic scale. So in class, we're not always going to work with elastic collisions. We will work a lot with collisions that are inelastic. So inelastic can be broken up into two classes. We're going to mostly use perfectly inelastic, but I'm going to start with inelastic. So the first thing here is that kinetic energy is not conserved. Kinetic energy is not conserved. Unless they tell you it's not conserved, but the change in momentum is conserved. So this is the clear difference here. And we're going to sum this up a few times because we got to know these definitions. So for a collision that is inelastic, the objects will not stick together, but of course we know kinetic energy is not conserved. But the two things that collide do not stick together. The opposite is true for perfectly inelastic collisions. The objects will collide and they will stick together, like a meteorite collides with Earth. A collision that is inelastic is something like if a minor car accident, right? You bump into each other and the cars separate, that would be inelastic. And perfectly inelastic is when they stick together. So you can imagine that in the initial scenario, you might have, I hope you guys can see this at the bottom, you might have mass 1 and mass 2, but in the final scenario, you might have something like a total mass, which is equal to the sum of the masses because now they've stuck together. So let's look at each of these situations on the next slide very specifically and see what equations we get out of there. Henry says for elastic, the delta P is also 0. Yeah, for inelastic, yes. In both scenarios, the change in momentum should be 0. The change in momentum should be 0. The only difference
Perfectly inelastic one?
For both, for everything here.
Okay.
For everything here, the change in momentum is equal to 0. The only difference here is that kinetic energy is conserved here and not here. So let me write it just to be very clear. There you go. So this should be the case throughout our collision situations if we're working with isolated systems. The only difference then is the change in kinetic energy. So let's take a look at the most common scenario that we will work with. Straightforward, the perfectly inelastic collision. So here you have particles that will collide head on and they're going to stick together. And then because they stick together, they're going to move with some common velocity after the collision. So as always, for any isolated system, the change in momentum is equal to 0. So here, the two particles are going to collide with each other. Notice we're given mass 1, initial velocity 1, mass 2 with initial velocity 2. They're going to hit, strike each other, and then stick and move together with one mass and with one common velocity. So the momentum is conserved. That's where you start. We start with that equation, and as always, I wouldn't skip a step. Take the time to write it all out. So this is the conservation of momentum. The change in momentum is equal to 0, which tells us that the initial must equal the final. And then you can write this out explicitly for each scenario. The initial momentums for each. So this is the initial momentum for scenario 1, and this is the initial momentum for scenario 2. And in some cases, one of the objects might not be moving in the beginning, and then that would go to 0. It'd be really nice, right? When things go to 0. Our total momentum then for the entire situation, you can name this anything you want. Usually in the textbook, they just use P final. Sometimes I like to, keep that going throughout my problem solving. So I'll write like a large mass, something like that, so that I know that it's the two masses combined. But it's really up to you. This is what you'll see in the book though. Okay, so now that we have this equation, the thing that is commonly asked for is what is the final speed of the combined objects? So we solve this for that final velocity, and this is a very common equation that you can use for an isolated system, for a perfectly inelastic collision. If they ask you for the final velocity, you can go straight to this equation, or you can derive it from here. It's good to know how to derive it though, because sometimes they might switch it up on you and tell you the final velocity and instead ask you for the initial velocity of the first particle. That can happen. So you just work this around. So this is as much as we can say about a perfectly inelastic collision. Remember that kinetic energy is not conserved here. Kinetic energy is conserved for a collision that is elastic. So that's the next one we're going to look at. And we're only looking at these two because these are the two common ones you're going to see. So for a collision that is elastic, oh God, for a collision that is elastic, both momentum and kinetic energy are going to be conserved. So here, you're going to have two particles that will move along the same straight line. They're going to collide head on, and they will leave the collision site with two different velocities because they're not sticking to each other. And that's the definition of elastic, right? Kinetic energy is not conserved, and usually they don't stick together. Yeah. Okay, so here's visually what we see. The first particle with the first speed and the second particle with its initial speed, and then they collide. That's the collision happens, the impact happens, and then they leave with their same masses, but they leave with new velocities. They each leave with new velocities. So how do we calculate this? We know the change in momentum is going to equal 0. Right? Change in momentum will equal 0. So we know that equation. And we also know the change in kinetic energy is conserved and will equal 0. And we know that equation too. Get ready for an equation dump. There it is. Now, this might look like a lot, but we've done this. We've done this before. And so here's the first equation that you see. The change in momentum is equal to 0 means initial equals final. And we have all of the initial components equal all of the final components. And based on what the problem gives you, you can now solve for one of them. Here we have the change in kinetic energy is equal to 0, right? Oh my God, my mouse is failing on me today. Okay, so initial equals final. All of the initial components equal the final components. And now we have these two equations where we could, if we needed to, we could sub one into the other and solve for it. It really depends on what the problem asks for. The good news is that those are the two common scenarios. So let me give you a full summary on the next slide. Voila. There it is. So first, you want to conceptualize, right, what's happening. Draw an image of some sort of the collision that is happening or the interaction of the particles and how it's happening. Then you want to categorize, right? Is this going to be a problem that is inelastic or elastic, right? Because that's going to tell you if you're going to be able to use the kinetic energy equation or not. once you've done that, now it's time to go to your equations. Now it's time to write down the equations and start filling in what you know and solve for what is being asked for. So for perfectly inelastic, usually they ask for that final velocity and you can solve for that. For a collision that is elastic, this is what you get from the change in momentum equaling to 0. Here you also have that the kinetic energy is conserved. And from the change in kinetic energy being conserved, there's a derivation that takes about 4 slides or 1 page and a half, something like that in the textbook, that will lead us to this equation. This equation is the relationship between the velocities in a situation where you have a elastic collision. Do you need to know this equation? No. You don't need to have it memorized. If you can recognize that you are in a situation that is elastic, then you could use this relationship. I wouldn't push it on you though, because one, I didn't show you the derivation, and I think you want to practice more identifying the situation and working through it with the kinetic energy. But deriving this takes about 4 slides to do. But this relationship is true and exists. The last situation, the one that is more common for us, is a collision that is inelastic. And here again, you have your change in momentum is equal to 0. And so the more common ones are these two with our stars that you'll see. Okay, I think we're ready for me to stop talking and try a problem. We're not even at the hour mark yet. We're doing really, really well on time. Voila, a problem. Okay, an 1,800 kilogram car is stopped at a traffic light and it's struck from the rear by a 900 kilogram car. The two cars become entangled, moving along the same path as that of the originally moving car. If the smaller car were moving at 20 meters per second before the collision, what is the velocity of the entangled cars after the collision? So we need to read this again, and you have to look for cues as to how this is a momentum problem and what is the situation. Here's the one that would probably be the one that would cause you the most trouble. The word is this word entangled.
That means that's inelastic because they touch each other and stay together.
Yeah, they're going to stick together. That's what that word entangled means. And there are going to be several ways that the problems are going to share that, are going to say that, right? The problems, they're going to say that they're linked, that they fused together. They might be nice and just tell you straight up that they stuck together or that they moved together, but they might not. So you want to recognize this wording. So an 1,800 kilogram car is stopped at a traffic light and then is struck from the rear. So here's 1,800 kilogram is big. So this is my big car, 1,800 kilogram. And he is stopped, or she is stopped at a traffic light. They're stopped, right? The smaller car was moving before the collision. Oh yeah, stopped. So this V1, I don't know if it's 1, but I'm just gonna call it 1 for now. It might change on the other side, I don't know. But this V initial is equal to 0. And then you have a smaller car, a 900 kilogram car that is going to come from behind along the same path. So it's horizontal, we'll keep it horizontal. And it's gonna be struck from the rear by a 900 kilogram car. So this one actually has motion. I'm gonna call it 2, even though I don't actually know if it's 2. And its motion is 20 meters per second. Yeah. So this is the initial. After the collision, they're entangled. So there's big car and little car, somehow together. And what is the final velocity then of this collision? So notice we have a drawing and we can start. And Randy saw that entangled means that it's inelastic. They're going to stick together. So we start with our change in momentum is equal to 0. And this is written as P initial equals P final, the devil's number. This is equal to P initial and P final. And now we can write out what is P initial. P initial is mass 1 times velocity 1. Oh, so they switched it.
1,800 times 0?
No, they switched the order of, okay, maybe I switched it. They call this 2. this 2, and this one 1.
So 80 or 900 times 0? Or
Yeah.
10?
So here you would have mass 1 V1 plus mass 2 V2 of the initials. And what you're saying, Randy, is that one of them is equal to 0, right? And they chose the heavier 1800 kilogram car that is stopped to be object 2. So this goes to 0, and that's why we only see mass 1 times V1. And then the final situation is the 2 stuck together and now moving in a final velocity. So this is the full equation now that we're solving. And now we can solve for that final velocity that they asked us for. And you see then that the final velocity, just moving things around, mass 1 V1 is that small 900 kilogram car moving at 20 meters per second, divided by the total sum of the masses, 900 plus 1800. And so the final velocity of the 2 cars now being entangled and moving with each other is 6.67 meters per second from the little car hitting the big car. Okay, let's try this. What if we exchange the masses of the cars? What if the 900 kilogram car is then struck by an 1800 kilogram car? You guys tell me before we even get the answer. Is it going to move faster or slower? In the first situation, the little car hit the big car and we landed at 6 meters per second. If the big car hits the little car, are they going to move faster or slower?
Yeah, if the
Faster.
speeds are the same.
Okay, I hear lots of everyone saying faster. Yeah. And Owen also faster. Yeah, so this is our intuition of motion. Our intuition of motion is actually momentum and not as we think of acceleration and forces. And so, yeah, you guys are correct. The final speed is going to be higher because the momentum of the larger car is going to have a greater impact here. Notice that we're not talking about the total momentums, we're talking about the specific final velocity. And so if we switch now, we use the same equation, but we just switch the masses around and we make this the first car, the 1800 kilogram car. You see that this 1800 on top is going to increase this number by a lot. Yeah. How are we doing? Do we feel like a 15-minute break, or can I go on can I make it till 11:30? Y'all tell me.
Can we take a break?
Okay.
I'll go for a break.
Let's take a break. Let's come back at 11:15 on the dot. 11:15 on the dot. Hello. Hello. I hi guys, hi Keon. I know I said 11:15, but in my head I meant 11:10. So we got an extra long break. And I hope you did some squats or something. I actually don't feel like sitting down anymore, so let us move up. Here we go. Hi Robin, hi Saja, hi Owen.
Sometimes I actually have I actually get sore from sitting. Like the next day I'll go, did I fall? You know?
Yeah.
Like my butt actually hurts, like, or there's a bruise or something.
Yes, exactly. And you don't realize that you've gone hours sitting down. Hi, Nathan.
Okay.
Yeah, you don't realize it. Let me move things back around here. So yeah, whenever you get a chance to move your legs or you don't have to sit, don't sit. Move around however you can. Before I got my standing desk, I would use like you guys saw yesterday, or 2 days ago, my tea stash, and I would make like a little fort of boxes, and I would put my laptop on top. Um, you know, use anything you can to make things comfortable for you. So those tea boxes came in useful. Um, yeah, Nathan. we gotta stand, move our legs a little. Um, but good thing again, I meant to say 11:10, not 11:15, and so we got a little extra time. I hope you guys um, actually felt like it was a break. Okay, so what we just did was solve a problem in one dimension. The only part that's left now for us to look at is, making sure that we can extend this to a two-dimensional problem. And so collisions in two dimension, everything will just extend to writing the x components and the y components for momentum. And you can analyze a situation just like we did before, but instead of looking for forces and acceleration, we're looking for masses and velocity. So let's look at this scenario here. We have two particles that are going to collide. Notice from the drawing all the information we can pull before the collision. So, very nice to identify before the collision. Particle 1 is moving with some initial velocity along this straight path. Particle 2 is not moving with any velocity. So here we could say V2I is equal to 0. We know this because there's no red vector, no red arrow that's labeled velocity. So this velocity will be equal to 2. Now they're going to collide and hit here just like you would maybe on like a pool table. And after the collision, notice again you have that clear separation. After the collision, the two masses are going to leave with some velocity. Here we see V1 final, and here we see V2 final. Now again, we know what to do when we see these velocity vectors. It was a question on the exam, right? Split them up into your x and y components. Resolve the vector into its components right away. So you'll know how to get the horizontal component and the vertical component. And you can make up, like some of you had to also in the exam, make up your own line, your own reference, and draw in your angle. And that's how you determine what is cosine theta, what is sine theta, based on adjacent and opposite and hypotenuse. So now with the before and after, you can go back to your equations and write them all out. So this is what we would see. Oh, question? No? Okay. So this is what we would see here. The total momentum equal to total momentum's conserved, so equal to 0 on the x and equal to 0 on the y. And now we continue the initial and final in the x. Then we write all of the initial components first, and you see again mass 1 times the initial velocity of 1. And if you were to write the second one, m2 v2, you would know that this V2 initial is 0, and so that's why it's not written there. But you could just write it out. That's okay too. I normally write them out and then cross them out. And so then what is it all equal to in the x component? And just like we did in our free body diagrams, we go along the x component and we look for all of the x's. V1 final cosine theta times the mass. Remember this here is mass 1 times P1 final in the X, right? P1 final in the X, and that is this component here, V1 final cosine theta. Oh, I'm sorry, that's just P is equal to, no one caught that. Someone should have caught that I wrote that wrong. I think because I'm standing, there's like a height difference and I'm, I don't know what I'm looking at anymore. So, oh, I erased the wrong thing. People, someone tell me what I'm doing. Okay, maybe I'm not back from break yet. That's what I think it is. Okay, so that's what that component is. There we go. Okay, so let's keep going, and then I'll get to Brad's comment, comprehension, and YF is oh yes, no, my comprehension at a higher height is messed up. It's messed up. Okay, so that's what this momentum is. I just wanted to make sure you guys know where this V1 final cosine theta comes from, and it's this component here. So the final then is the final component of the first particle in the X and the final component of the second particle also in the X. And here we see the X component here too.
So this means that like the initial is equal to final?
Yeah. Yeah, and any way you break that up in component form or particle 1 to particle 2, the initial and final will equal each other. And so we can do the same. Oh, control Z, yeah, I need to do a lot of control Z. So we can do the same for the Y components, right? P initial in Y equals P final in Y. So initial equals final. And the whole thing, the P initial in Y, you guys can look here on the initial. There is no Y component, right? There is no Y component for either one. This one's velocity is 0, and this one doesn't have any velocity in the X. So that's why you get 0 for this component here. Now the Y final, now we have to look at everything in the Y direction. And the first one is mass 1 times that velocity component in the Y, and the velocity component in the Y is V1 sine theta, and this is positive, it's pointed up. The second component, we see it here, pointed down, so that's why we have the minus sign, and we continue with the second component. The mass times the final velocity's Y component. I'm finally getting it together here. And then of course, if we looked at, if this were a situation that was elastic, we would know that the kinetic energy is also conserved, and we could make the same statements for kinetic energy. And so that's what we have here. Oh, let's go pink. Kinetic energy is conserved for elastic, change of kinetic equals 0. So the initial components, notice that this is kinetic energy. It is not a vector, so you do not break this up into components, only initial and finals. So the initial components are only from the first particle because this is equal to 0. So 1/2 mv squared of the first component, the second one would equal 0. And then the final components, we just write them with their scalar values for this final component and for this second velocity final component here. So 1/2 mv final squared for the first plus 1/2 mv final squared for the second. So all we did here was break them up into its components. And again, you can only do that for the momentum part because momentum is a vector and kinetic energy is not. And so this is the summary for the two-dimensional motion. You use these equations just like you did with vectors and breaking up the vectors and breaking up the forces. And so here, the same, you want to go through the same process, drawing some sort of image, figuring out what is the physics in the situation. Is it elastic, perfectly inelastic, or inelastic? And it should be obvious by the problem and the way it's written. Yeah, it should be. And then, but you have to know these definitions, right? as long as you know those definitions. Then you pick your equations and you start plugging things in. So for two-dimensional collisions, when the change in momentum is equal to 0 for isolated collisions, you want to make sure to break them down into their component forms. Resolve the vector into components, and this will help you solve for any unknowns that you might have. And then finally, you can solve it. So if we're ready, let's try a problem. Okay, so collisions at an intersection. A 1,500 kilogram car is traveling to the east with a speed of 25 meters per second, and it collides at an intersection with a 2,500 kilogram car traveling north at a speed of 20 meters per second, as shown in the figure. Find the direction and magnitude of the velocity of the wreckage after the collision, assuming the vehicles stick together after the collision. So first, I would analyze the drawing that they very nicely provide you, and also start to make a connection between the wording here and the drawing so that you can make a drawing whenever you need to. So the first car is traveling east with a speed of 25 meters per second. And here's the first car traveling to the east, right? And let me remind you in case this, is any form of confusion. Traveling east at 25 meters per second. So this is moving along the I-hat direction. The second car then is going to travel, is 2,500 kilograms, and it's going to travel north, at a speed of 20 meters per second. So north means J-hat, and that's why we have the J-hat there. So we have the full vectors here. Yeah, and then it says that at some intersection, they are going to collide and then leave moving together with some final velocity. And they want us to figure out what is the direction and magnitude. So what is theta and what is the magnitude of this final velocity? And we know how to do this. We just need our components of everything, right? Okay, so notice that they stick together. So this is nice. We know how to calculate for these things. But we can just start from the conservation of momentum. Let's bring it all over to the other side, and we'll start by looking at everything in X and then everything in Y. Very nicely, this one only moves in X and this one only moves in Y. How nice of them. Okay, so we look at the change in momentum here for each. And the change in momentum in X is equal to 0. So that means the sum of the momentums in X equal the sum of the momentums in X final. So in the initial situation, the only thing that's moving in the X is the first car. Only thing moving in X initially is this first car. So that's all we have in the equation, M1 V1 initial. And in the final situation, the two cars together are moving with some mass and then with some X component of the velocity. This is X, the X component of the velocity, VF cosine theta. In the second situation, when we look at the Y components, again, the change is equal to 0. The initial in Y is equal to the final in Y. The only initial in Y is the car that's moving to the north, which is the second car, right? Let me remind you, only this car is moving in the Y direction. So the other one is equal to 0. And the final situation is the sum of the masses, again, some big mass, and the final velocity component in the Y. Now, up to this point, you've done all the physics. Now it becomes just about manipulating the equations to get the direction and the magnitude that we need for the velocity. So what do we need for direction, or what is our goal when we're solving for direction? Anyone out there? Direction, what are we solving for? Just tell me the variable.
The theta.
Yes, theta, and I hear theta, and I see theta in the chat from Henry. Thank you. So looking at these two equations, I'm gonna just number them, equation 1 and equation 2. You want to solve for theta. There are several ways to solve this. The longer, like very formal way to do it is to set everything equal to V final. Set everything equal to V final here, and then equate them. You're gonna eliminate a lot of variables. if you're very comfortable with the math, perhaps you can just recognize that you can divide the two equations and eliminate things faster that way. So I'm going to show you how I would do that with my blue pen. So you have equation 1 and equation 2, and you have cosine theta and sine theta. A quick reminder that we know tangent theta is sine over cosine, I think. Opposite over adjacent, yeah, sine over cosine. So I'm gonna take equation 2 and divide it by equation 1. You can write the two out and just divide them by each other. This whole thing cancels out. And now I can write sine theta divided by cosine theta is equal to m2 v2 divided by m1 v1. That's just taking two equations and dividing them by each other. That's a shortcut that you can get comfortable with. Or you can set each one of these equal to either v final or this whole component here. Set each equation equal to this, and then equate the two. When you equate the two, you'll get the same exact situation here. And so this is the equation that we come up with. The quick way of doing it again is taking equation 2 and divide it by equation 1, or set them equal to one like component, and equate the two equations. Okay, so now we can write this shortcut, sine theta, cosine theta, as tangent theta. And now we can solve for theta at the very least, right? Theta then is the inverse tangent of this component here. And we know all of the initial variables. Mass 2, the initial velocity of the second car, the mass of the first car, and the initial velocity of the first car. And now we have our angle theta from that horizontal is 53.1 degrees. And so from here, you're asked to find V final. What is the magnitude of V final? We don't have Vx final, Vy final. Perhaps you could solve for it, but you can also recognize that V final is in both of your equations 1 or 2, right? V final is right here. So you can take any one of those equations and plug in what you now know for theta and solve for V final. So here we took equation 2 and plugged in theta that we just solved for, and now you can get your value for V final. This is a more direct way than looking for the other components. How are we doing out there?
Fantastic.
I'm glad to hear it. Yeah,
Right
not bad. I hope it's sinking in. Okay, it should sink in. And again, you know, I would be very, very like incredibly impressed if you got this all from just listening to this lecture. Typically, you know, you got to review it 2 or 3 times minimum. Even me, always 2 or 3 times. So good news, everyone. We have finished chapter 9, and this is this is what you need to know, and the last part that will be in the exam. Yeah, and like Owen says, this is how usually physics goes, and usually how a lot of science goes. And it's not that it doesn't reflect, like, you know, your curiosity or your passion for science. It's the nature of science. We will not go from the beginning to the answer right away. It's a journey. It's a long, long ass process, and you got to take your time with it. Embrace it, you know, like athletes or like working out. It's all there. So we have finished chapter 9. We have just enough, we have plenty of time, but I'm pretty sure we will finish early. Yeah, that was fast, Andrea. I think so too. We really want to get the idea of momentum and collisions kind of, you know, we already know vectors, we already know 2 dimensions, we already know Newton's law, and we're very comfortable with things changing over time. So now the concepts are just a little newer and applying them. So it's good. I'd like to transition us to our second lab for the week. And I know that might sound like a lot, but the second lab of the week is just going to be calculating and practicing momentum and collisions and kinetic energy. It will not involve a lab report. It will only involve the lab manual. You plug in your data and you solving for it. And that, I hope, should help you with managing the other assignments that you have. So give me a second to pull things up. And yes, Henry, I also made it due Monday because of this shorter week that we have. Um, it's so crazy. We have a shorter week, and it's the first time we're doing three chapters. But again, I've been doing this for quite a few years, so we got this under control, guys. I'm gonna, if you have Canvas open, you can refresh the page, and you will see the lab now. I'm going into
lab now, you're saying?
Yeah, it'll be posted now, and I'm gonna take it into student view so that I can show you guys what it is. So you should be able to see it now. Refresh your Canvas and just make sure you can see it. But I'm going to walk you through it right now. If you feel like you know the lab and you want to, do it on your own, adios. Do whatever you'd like. I'm going to keep recording and go over the lab, and that's it. Okay, let me share my screen. Oh no, is it the right one? Yes. Okay, and let me get my chat open so I can see you guys. Okay, I think I can still see everything. Okay, so if we go down the line here, we have our lab conservation and linear momentum. And again, I think these are pretty fun because this one does not involve a report, and it only involves you colliding things in slow motion and writing things down. So again, this lab is due by Monday, not Friday, but Monday because of the shortened week we had. Always start by looking at the simulation and looking at all of its features so that when you read the lab manual, the features or the buttons are familiar. Read the entire lab manual to make sure you answer all the questions that are in the lab manual, and then submit as soon as you can. So let us look at the lab manual really quickly first, and then I'll open the other thingy. Okay, I'm gonna do. Okay, let's hope that is centered enough. Okay, so here we have our objective and we have our theory, and now we recognize this equation. The force is the change in momentum over time. And so what you're gonna do in this lab is set up collisions, and again, they're slow motion collisions, no, small budget here. You're gonna set up different collisions for different masses and see the results, and hopefully you'll see the concept of conservation within these results. And so the first one you're going to set up is a collision that is elastic. And notice that for the collision that is elastic, mass 1 will equal mass 2. So you're going to click on the link, and that'll take us to this, this simulation. And then you're going to click on more data so that you can see more options. And this one, very nice, has the screenshots. You're going to select the elasticity of the collision to 100, just dragging that blue triangle. And you're going to select mass 1 to equal mass 2 by setting them each to 2 kilograms. You're going to select position 1 as 1 meter, position 2 as 2 meters, and then select the initial velocities as 2 meters and the other one to be 0. And all of the data that is written up here is also shown in the screenshot. So once we set that up, you are going to hit play, and I'm going to walk you through that. The collision is going to take place between the red ball and the green ball of equal masses, with one initially at rest. So the red ball is going to collide, and then things will stop, and M2 will move on in the same direction of M1 before the collision. It'll make sense once we play it. So click on play, and then after the collision, click pause and record the values of the final velocities in your table. So in your table here, you want to record everything that was given to you. The initial values are already set up for you. So the first initial value is 2 meters for the first ball, and 0 meters per second for the second ball. Then you want to record the final values of the velocity and calculate the momentum based on the masses that you're given. You can calculate the initial momentum, and then you can calculate the final momentum based on the final velocities that you have. You will then take a ratio of the final and initial momentums, and you'll see some values there. And then you'll do the same for kinetic energy. You can calculate the initials right away because you have that, and then you can calculate the finals once you get that final velocity, and then you'll take a ratio again. That was a mouthful. Okay, let me go to the top and we'll click and we'll go. Uh-oh, oh hell. Oh no. Does everyone else see this too? Oh no. Don't block it, don't block it. Where's that button? This one. Where do I click on? I can do this when I don't have an audience. Block slides. No, do not block slides. They did discontinue it, but this should still work. Okay, well, I'm going to look for the link. Does it work for anyone else? Tell me the truth. Anyone else out there? Just try. Yeah, just try. Okay, so I will check on this, but you guys tell me yeah, I totally know the whole scenario with Flash, but this should have been a Java-based one. So I am going to take a moment to look for the Java-based one. If the Java-based one does not work, I'm either going to give you guys numbers, or you might not have to do this. We'll find out. But keep an eye out for an email from me today, probably in the next hour. I will let you know. But yeah, it should have been a Java-based. I'm pretty sure they have a Java-based equivalent, and I'm just going to find it and give you guys the link for it. Yeah, it's totally a Flash thing. I 100% get it, and if all of you are getting it, that means the thing is Flash-based. So I'm going to go look for a Java-based simulation and get back to you guys on this, hopefully very soon. It should be very similar simulation. If it's not, well, whatever, we tried. Yeah, that's all I can do here. So guys, keep a lookout for your email in the next hour. If I don't find something in the next hour or two, whatever. Maybe I'll go look at the old values and give you the old values and see how that goes. Yeah, thanks for bearing with this. I changed all of them to Java-based. That's all I have for you. That was not planned. So our lecture and lab is done for today. Please keep a lookout in your email for a message from me. Yeah. Get the lab going for the other one and practice the homework. Email me if you have any questions whatsoever. I'll do my best to get to you quickly. Yeah, that's all I got for you. Have a good week. This has to be a good sign. Good vibes to all. Have a good weekend, guys. I'll see you all. Bye, Nate.
Have a good weekend. Thank you, Professor.
Have a nice
Bye,
weekend.
Jan.
Hey, can I ask a question?
Yeah, of course. Let me finish and then I'll stop recording and I'll go to you, Randy. You'll be very first one. Bye, everyone else.